All right, so the next one kind of on the same theme. Looking for some video on refrigeration cycles showing where you would measure superheat and subcooling, and then also explaining parts of an expansion valve. I grabbed a picture here, like the equalizer line, for example. I saw a few questions on past exams. Cool. So absolutely, we can do that. Let's start with the first part, which is where would you measure superheat and subcooling? And we're going to do that in two ways. First, let's do it on a pressure enthalpy diagram. And then we'll do it on a schematic. So we've got our vapor dome for our refrigerant. And we've got our entering compressor. Well, actually, it's already interesting, right? Because normally when we draw the refrigeration cycle, we like to draw state one as being right on the saturation curve. But there's an assumption in that, isn't there? What's the assumption associated with selecting that point to be right there on the saturation curve? Right here.
No superheat, no subcooling.
No superheat for state one, and this, right?
Yeah, so no superheat at state one and no subcooling on state three, the way you have it drawn.
Exactly. Exactly. So this is not real life. This is an ideal case. It's a case that we often assume, at least as a starting point for many problems, and sometimes we don't have to go any deeper than that. And that kind of gets us where we need to go. But in real life, and even in some problems where they want to make the problem a little bit more realistic, point one will be selected out here to the right, which is to say that there is some superheat. And then state three can be, isn't necessarily, but may be out here to the left in the subcooled region. So if we were going to measure superheat and subcooling, those would be the locations. Here is where we'd be measuring how much superheat. And here is where we would be measuring how much subcooling. Now let's also, just for absolute clarity, look at that on a schematic as well. Got our compressor. Nobody can make fun of my freehand doing it live today. All right. Okay, so entering the compressor, this is the compression process from 1 to 2. So this is our state 1. This is our state 2, 3, and 4. So again, we're looking for superheat here, if any, and we're looking for subcooling here, if any. Obviously, this is flowing like so. Okay, anything else on the first part of that question? Does that make sense? Okay, so for the second part, explain the parts of an expansion valve. I'm not an expert on these, but I think I can answer the spirit of this question. So it fundamentally, I just looked this picture up on Google Images and threw it up here. I thought it would work for us. We have our refrigerant inlet. So this is coming out of the condenser. We have a saturated mixture we either have a saturated liquid, let's go to our diagram at state 3, or we have a mixture that's almost liquid, or we have entirely liquid if there's subcooling. And in real life, there would always be at least a little bit of subcooling, or we would be, very, very confident that we have reached the left side of the curve. I don't think it's common to have a mixture, because if you have a mixture, that means you haven't condensed all of the refrigerant, which means you're not getting the maximum capacity out of your condenser. So that's not a very good operation. So you do want to see state 3 come all the way to the left and potentially even beyond the left side of the saturation curve. Okay. So that being the case, State 3 is what's entering this inlet. And then this is the outlet, leaving the expansion valve now as a low pressure vapor at low temperature, and going to state 4 to enter the evaporator here. And how does this work, right? So the way this works to make sure that we're flowing the right amount of refrigerant around the cycle, we want to make sure that we've got that mass flow rate dialed in just the right way. So mass flow rate of refrigerant going around the cycle in a closed loop, such that we have the superheat that we expect. Okay, that's the goal. So here's our state 1, our superheat. Maybe there's 5 or 10 degrees of superheat, whatever the case may be. That's an operating point that the system is meant to maintain. So how does it actually achieve that? And how does this expansion valve lend itself to doing that? Well, this sensing bulb is landed on the refrigeration piping around state 1, somewhere around here. So I'll just put a point there. And that's going to be our sensing bulb. And then there's a capillary tube that runs back to the valve. And that capillary tube is also closed. So it has refrigerant in it as well, but it's not flowing between the closed loop and the capillary tube. It's separate. It's just there to sense the temperature at state 1. And if it gets too high, then that heats up. And when it heats up, it expands and it pushes down on a diaphragm right here that drives a pin down, which causes an orifice to open, which causes a little bit more refrigerant to flow through the cycle. And when more refrigerant flows through the cycle, what happens? Well, we know that if we just analyze the evaporator for a second, we say Q dot for the evaporator, Q dot in, the refrigeration effect. That's a constant. That's a fixed load that always has to be the same, is equal to the mass flow rate of refrigerant times H1 minus H4. So that heats up, that pushes that diaphragm down, that opens up the orifice, that lets a little bit more mass flow rate of refrigerant to flow. So that's going to drive m dot refrigerant up. And this is fixed. This is a constant. And H4 is what it is. It came through the expansion valve, and you can't change that. Sorry, H4 is fixed. So the outcome is that H1, well, this delta is going to have to be a little bit smaller, which is to say that H1 is going to have to be a little bit smaller. So it drives the amount of superheat down just a little bit, right? You can imagine this dynamically adjusting to maintain the level. And then the opposite is true as well. If the superheat then gets too low, then that means that the refrigerant in the equalizer line is going to slightly cool, which is going to reduce the pressure on that diaphragm, allowing it to lift up, which closes the orifice, which tightens up and reduces, adds some pressure drop here, reducing the mass flow rate. So in that case, the mass flow rate goes down and H1 goes up. And this is a constant dynamic process that balances the amount of superheat. So your question about the equalizer line, that's the same thing as this tube, is my understanding. Just 2 words for the same thing. Now, this is thermal expansion valves. There could be other types. There could be electronic things out there, and I don't know that I have all the information about those or that you need to. But fundamentally, I think the big idea here is that the expansion valve is controlling the mass flow rate of refrigerant, which has a direct impact on how much superheat is being observed at state 1. And if you want to control that, then you have to be able to vary the mass flow rate of refrigerant. Not to say that it needs to have a wide operating range, but it needs to be able to slightly adjust and correct to stay in bounds.